Okay, guys. So we are going to start with this first module. And the things that we are about to do is the thermodynamic system. All right. And as I said, once we're done with this module, we're going to take the first exam. So that means the exam that we're going to do probably is not going to be lining up with other subjects. And I think that's going to be beneficial to you, I think. Yeah, because you guys can, have time to study some other subjects and then, all right, just get things done with the physics. Or, all right. And in general, you guys can pick the not the final, pick the exams dates. So we can, when close to the exam, then we'll come up with the votes. When are we going to take the exam? Okay, sounds good. All right. Okay, so what we are about to do here is the thermodynamics. All right, and for even though the lecture say week 1, sometimes we might not be able to do within the week, or maybe it's faster than a week. So who knows? All right, but let's say this is a lecture handout number 1. So we're going to start easy. I hope today, just sort of get to know each other a little bit, and how things go, and then what's about to happen. So we're going to talk about thermodynamic system. We're going to discuss what is actually temperature. Whoa. All right. And then we're going to start with some weird stuff that only physicists can do. The Zeroth Law of Thermodynamics. It's kind of like, okay, they already done other laws, then they don't know what to do. So they would put like a more fundamental law in the zeroth order. That's kind of, all right, feel bad about physicist people. All right. Okay, but anyway, so we have gonna have some, analytical or numerical calculations in the topic of thermal expansion. That is a consequence of once we know what happens to the material from the perspective of temperature changes and everything. So we have thermal expansion. All right. And once we get that done, then we're gonna have a look at some very sort of, familiar properties of matters. We're going to start with the state of matters, but the one that we're going to focus on the most is going to be gas. The reason that we are going to focus on gas because we have gas laws, that we have an ability to calculate things perfectly, or sort of like we have some equations for us to explain gas behavior and all this stuff. So that's kind of nice. And then we're going to end this portion with the specific heat and latent heat. So we're going to learn a little bit about heat and about heat, how things go with heat, what is heat, what heat is going to be doing, all this stuff. So that's all about heat. Okay, sounds good. All right, so first, all right, let's sort of like hear me out here. Why do we need this topic at all? Right? Because sort of like Ajahn, I have done, Newton's law. We do like, translation, energy, momentum, rotation, angular momentum, moment of inertia, center of mass, like impulse. I mean, we have done many, many stuff in mechanics, but why do we still need more? We still have thermodynamics. Why? All right. The word here that we have right here is dynamics. So there is some changes going on. There's some dynamics going on. But you have a thermal aspect of this one that you really want to get into. All right. That's the key part. The sorry, the thermal part. All right. That's the one that we want. The point is that, guys, how many oxygen molecules running around you right now at this moment? You just look around in your room or whatever your location you are at. What do you think about the numbers of oxygen molecule? You also breathing in, you exhale carbon dioxide, all that stuff. But in terms of the numbers, what kind of numbers that you are dealing with right now? Give me an answer. Whew. Just kidding. You're not getting any point or anything. All right. What do you think? What kind of numbers you are dealing with? How many oxygen molecules, let's say in my room right now? Any suggestions? You know, you're awfully quiet right now. Okay, all right, thank you. All right, that's one response right here. It's more than that's kind of safe way of answering this question. More than, so that's like, you know, upper limit is crazy. Oh, that's one crazy number it's throwing in right now. 10 to the 23rd. Very good, very good. Getting bigger is super big. All right, so that is great. Thank you for the answer. And you were right, is crazy number. Even though you talk about like, you know, 100,000 or a million, that's still a lot. But if you're looking at the numbers that your friend just type in, you have a familiarity with this number. Is the Avogadro number, right? Yeah. Familiar with that? Let me put the subscript A for that. And that's about 6.02 times 10 to the 23rd. Here comes the next question. Let's say I would like to find out the kinetic energy of the oxygen molecule. How would you do that? Well, that's no big deal. The kinetic energy is just 1/2 mv squared. So that means if you really want, all you need to do is just try to somehow calculate or somehow detect, observe the velocity of the oxygen molecule, and then you just plug it into this equation, right? That's no big deal. But then if I say about, hey, once you get that one, I want them all. I want the total kinetic energy of the oxygen molecule in this room. How are you going to do it? Well, Ajahn, no big deal. Just sum them all. Whatever the numbers of molecules you're dealing with, just sum them all. But that's all right too, right? You can sum them. That's no big deal. But then are you serious that you're going to sum like million? How many millions is that? And then another 100,000, 10 to the 23rd. Are you going to do that? It's, well, even though it's not impossible, but it's not doable. All right. First thing first, how are you going to be able to detect the velocity of all those oxygen molecules? That's first thing. And the second thing is, once you, even though you have, you know, put up the camera, make sure that, okay, every time the oxygen molecule passing by, you detect the velocity, plug it in the formula, calculate the kinetic energy, all this stuff. But these things changes all the time. The oxygen, the molecules will knock each other, bounce from the wall, the ceiling, the floor, and all this stuff. These things are dynamics, right? So they are changing all the time. So that means you probably not going to be able to calculate the total kinetic energy of these molecules from the perspective of Newton's approach. 1/2 mv squared doesn't seem to work. You guys see what I'm going at right now? Right? We have limitation on application of the Newtonian physics. It's not because the Newtonian physics is at fault or it doesn't work or the theory is wrong. No, because our capability is limited. But we still want to answer this question. I want to still get the answer. I want the answer, guys. It doesn't mean like we cannot do, but doesn't mean that we cannot answer. So the question is how? How can we come up with the total kinetic energy of the air molecules in this room? The answer is measure the temperature. Okay. Isn't that cool? ไม่ว้าวๆ ไม่ตกใจ So that's the point. The point is, instead of going through the fine detail of stuff, no, you only need a single parameter. And it turns out only this single parameter will eventually lead you to the answers of the total kinetic energy of all the gases in this room. Believe it or not. And hence, this is what we are talking about. We are talking about the thermodynamic system. It's the system that composes of like millions of particles that we are not able to apply Newtonian physics directly, but we have another way of approaching it. And the approach, we're going to approach through temperature, heat. And eventually we're going to lead everything back to the energy eventually. All right. So that's sort of like give you a motivation of why we need this, because we would like to take care of other things, not just like throwing a ball onto the top of the building and find the speed. You know what I'm saying? Like, it's kind of weird, right? We're not gonna doing that. All right, but we want to do something else as well. And those are the thermodynamic systems. So it's a system that we can deal with them macroscopically. But those information that we can detect or we can measure from the macroscopic level will tell us something about the microscopic level's properties in a collective way. The reason we need the collective words is because here we go. It's crazy. It's like 10 to the 23rd, right? Who would be able to do that one by one, right? I'm not going to be the one who do that. So we need statistics. It has to be a stat. You do a million stuff here. So statistics works flawlessly here. Okay. Plus, everything that you have learned from statistics, this is the good system to apply to, because the population is huge. And everything that you're doing here is going to be almost theoretically perfect right here. Isn't that cool?
Okay.
All right, here we go. So I hope you understand what we are trying to get to. Now let's dig a little bit deeper into what does it mean by temperature? What does it mean by thermodynamics, equilibrium? You did before equilibrium in mechanics. Okay, the force left, right, up, down, they all cancel out. I mean, the net force equal to 0. But what does it mean in the thermodynamic system? Because now we're going to rely so much on the temperature, because now the temperature will be the key. Every time that you put two objects in contact, and if those two objects having different temperature, then we're going to say they are in thermal contact. You guys with me now? So remember back in the day that you did, okay, let me draw this one here, right? You have a box, there's a dude here, try to push the box with the force F, blah, 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 right? The key is you don't care about the temperature of this dude, right? I mean, you get sick or you get any flu or anything. You don't care about the temperature of the box. All you care about is what is the force. So that's why you left the thermal part back in the day of Newtonian physics. But now we're going to include that into our dynamics here. Okay. So what we are doing over here is, if I say about, hey guys, this dude here is 37 degrees Celsius. The box is at room temperature, is at maybe 25 degrees Celsius. So once the hand of this guy touches the box, you guys know what happens. Yeah, there will be some energy flow from the dude to the box, right? Because the dude is hot. The box is cold. So there will be something flow that you call it the heat. There's some heat flow. So actually there is something going on already before you applying any forces. And that is thermal contact right there. See, so the temperature play a crucial role here in this topic. You need temperature. Okay. And the easiest device that you probably have, used before is thermometer. So every time they put a thermometer into testing or measuring some object's temperature, that's when you put two objects in thermal contact. And then you wait, and then you wait until everything's just sort of sharing the same temperature. And that is your thermal equilibrium. You guys with me now? Okay.
Okay.
Sounds reasonable. Okay, at this point. So, all right, and that's it. So you get another kind of equilibrium. You get another kind of contact. Everything relied on temperature. Okay, and that's the sort of like starting point of thermodynamics right here. And here comes the Zeroth Law of Thermodynamics. It says, very boringly, if an object A and B are separately in thermal equilibrium with another object C, then A and B must be in thermal equilibrium. Wow. And you guys just like, what is going on here? It's so common sense. And that's how the thermometer works, right? You put thermometer, you check temperature of mine, 37. You check temperature of your friends, 37. So if I and your friends just shake hand, we already in equilibrium. They're not going to transfer anything anymore. Something like that. Okay. So that's what it is. That's it. Done. For zeroth law. Forget about it. All right. We don't need to worry too much about this at this point. But then once we have the temperature, now you must have a way that you can measure the level of the temperature. You know, the hotness, the coldness and everything. Yeah. The hot objects has a high temperature. The cold one has a low temperature. You guys know this. But what about the scale? What kind of scale you want to use? Right? Back in the day, but people learned so much about, you know, water and everything. They don't know what the temperature means at that time. They don't know the atomic structure of matters. They don't know anything. So they use water as the main system to study. So that's why they set the freezing point to be, let's call it 0. The boiling point, let's set it to 100, and then you'll be done with the Celsius scale. All right. But that's not what it is nowadays. What you have right here is you have absolute temperature scale. You have heard of that. You probably have done chemistry before, right? And you probably have some devices to show you, hey, if you have a gas or the stuff or the gas pressure drop down to 0 at the whatever extrapolated point, if you do some experiment, blah, blah, blah. But heck, what is the absolute temperature scales, guys? What do you think? What do you think is the absolute temperature scale? After you have sort of me talking so much about, you know, heat, temperature, energy, kinetic energy, the total kinetic energy of the system, on and on. I mean, you have listening to me for like 20 minutes already. What do you think the absolute temperature is supposed to be? We don't have to go through all this complicated stuff. Very good. That's one answer coming in. No energy at all. All right. So let me give you a reverse idea. Okay. If I have an object sitting here doing nothing, and this is just the only object in the universe, and this is just a single point, think of it like, you know, one piece of stuff, no internal structure, nothing. All right. And suddenly I give this some energy. Maybe I just light up a light, which doesn't make sense to light up a light in a vacuum or anything. But anyway, all right, let me shoot a laser light into it somehow. I'll just give this particle some energy. I'm just like, all right, I'll just give it energy. What happened to it? What do you think? I give this particle some energy. And as you can see, I'm not pushing it. I'm not doing anything. I'm just trying to laser line on it. Well, shining a laser light, I mean, you can think in terms of the Newtonian physics anyway. But the point is, let me give this particle an energy. What does it do with that energy, guys? Yeah, you're right. Whatever you're thinking is correct. It just have to move. There's nothing else it can do. It has no internal structure. It has nothing in it. Once it receives the energy, the only thing that it can do is just take that energy and run. Take energy and run. It's like grabbing money and run. No, it's taking the energy and run. That means you are getting kinetic energy. You guys with me now? So that means at the beginning that when this particle doesn't have anything, it doesn't have energy. That's when you have 0 absolute temperature. The K that I put in there, that's just the unit for the absolute temperature scale. We call the Kelvin. So when the particle does not have any energy, like your friend just said, that's where you are at 0 Kelvin or absolute 0 temperature. Does that make sense now? So that means once it's moved, it will represent greater than 0 temperature. But here comes, let me give you, this is like a spoiler or anything. We jump from the zeroth law all the way to the third law of thermodynamics. It turns out this is not allowed in our universe. our universe do not allow 0K. And that means everything in this universe must have temperature larger than 0. You, of course, we are living right now. We have greater than 0 temperature, definitely has to be. But you can cool it down as much, but you cannot freeze everything down to 0. So that means everything in this universe must be moving somehow. So I hope by saying so much about this whole stuff, you understand what I'm trying to get to. What I'm trying to get to is this: temperature has a direct connection to the energy. To be specifically talking about this one, to be exact, is the kinetic energy. So every time you talk about 0 temperature Kelvin, yeah, the 0 absolute temperature, that means 0 energy. That means no movement. That means no kinetic energy. That's where the absolute 0 lies. However, third law of thermodynamics says is an unattainable temperature. Nothing in this universe can be perfectly still. They have to move a little bit. And that has some connections with the quantum physics later, that, things always, shaky, moving around a little bit. So there's no way for you to be able to reach 0K in this universe. All right. So I hope you get these connections and what does the temperature really mean. So I think at this point, you should think of the temperature as the connections or a vessel that links to the energy of the system. That's what the temperature is. Okay, sounds good. All right. And to be able to convert between Celsius scale and the absolute scales, all you need to do is just add 273 approximately, or if you want to be a little bit more accurate, it's a 0.15 to the Celsius scale. You will get the absolute scale. Okay, that's easy conversion between the two. So the good thing about the Kelvin scales and the Celsius scale is the scale resolution are the same. Okay, so that means changing 1 degree Celsius is the same thing as changing 1 degree Kelvin. Same thing. All right, so that's nice. Okay, all right. So, all right, we don't need to worry so much about the Fahrenheit. I think the only country left that using this one is USA. So, all right, we probably have a conversion between them if you really want to. All right, but I think maybe the good thing to know is just like 40 below for the Fahrenheit is the same as the 40 below in Celsius. So that's kind of like, tip of the day. All right. Okay. All right. And I think it's a good point to take a break right here. Sounds good. All right. So we're going to take 10 minutes break in between, and then we'll come back with more of the thermodynamic stuff. And now we're going to throw in some, calculations that you have been missing so much. All right, guys. So let's take a break. I'll see you 10 minutes from now. Okay. All right, then. So welcome back, guys. So what we're going to learn back. Just welcome myself back. Okay. So what we are about to try to understand, and give you a test of what is about to happen is just looking at some simple stuff that happens from the change of the temperature to the material. And it's just the thermal expansion. And we can understand this one a little bit, more easily now, because we sort of understand that when you have a higher temperature, mean higher kinetic energy, this mean higher movements. So when you have those stuff going on in the back of your mind, then every time that things get higher in temperature, means the movement in the microscopic level is more. So that means the spacing between those particles or those molecules that's building up that material is going to be a little bit spaced out. Does that make sense? So it's going to get a little bit further apart when things are moving a little bit further. So the idea is just like, if you standing in the room with your friends, like let's say shoulder to shoulder, and then once I turn off the air conditioner, for example, and then it's like, okay, the room is getting hotter and hotter. It's like it kind of like annoys with the friends around you. It's like, hey, can you just, move away a little bit? It's getting hot in here. And that's where the separations between particles is greater when the temperature is higher. All right. But anyway, that is just, well, a normal circumstances. right? That means, right, right now there are so many stuff going on in the microscopic world. So there are something that might not follow this simple logic, but at least for the material that kind of follows, you can expect the expansion. Things get larger when the temperature rises. That's the whole idea. All right. So let's look at the scale of the temperature a little bit before we move on to calculating the expansion of the material. So this is what it is. Even though this one is referenced from the textbook, the lowest temperature is like a sort of like 10 to the negative 7. But I think right now we can go down to the sub Kelvin temperature now. I mean sub nano Kelvin. So it means it's go down to 10 to the negative 9, 10 to negative 10, and other stuff. But of course, it's not going to go through this super small temperature by using like a refrigerator or anything. Yeah. That's not possible. We're going to have to make sure that we are able to stop the movement. So that's why you might have heard of laser cooling, the cool stuff with laser. So the point of the laser is not, it's not heating or anything, but it's you use the laser to try to, let's say, okay, you have a particle over here that you want to cool down. But the thing is, you shine the laser light into it. And then the way is you shine the laser light just to sort of like, balance these particles so it won't move. So it's like you have to shine the laser light from this direction, that direction, left and right, up and down. Now you can imagine this, what is going on. You try to sort of like hold these particles as still as possible. You want it to stop moving by using the laser beams. That's the whole idea. All right. So that's why next time you hear the word of laser cooling, now you know it's related to the movement of those particles. You want to stop them to make it colder. Okay. All right. So that's how you get very close to 0 Kelvin, but definitely you're going to be able to touch 0 Kelvin. That's not possible. All right. And move up from there, you have like all those liquid helium, liquid hydrogen, liquid nitrogen, the one that you may be able to use it to make some ice cream now, on and on. That's somewhere around up to about 100K. All right. And now when you move on to room temperature, that's around 300K, let's say. All right, about 300 Kelvin. That's approximately. And then now you move on hotter and hotter. Maybe that's where the copper melts. That's when you reaching somewhere around like 800 Celsius or about 1,000 Kelvin. Surface of the sun is somewhere about 1,000 K. And now if you actually on that sun, you have like a solar corona, the one that's just all like, splashing around on the surface of the sun, that's already 1,000,000 Kelvin. Interior of the sun, now you have like a nuclear processes going on. There's some nuclear reaction inside that's up to 10 million. And then the hydrogen bomb, yeah, that was like now at the center of the bomb, you can reach as high as 100 million Kelvin. All right. So that's sort of the scale that we are looking at. And of course, usually we probably somewhere around here. Okay, somewhere around there. All right. So we're dealing with somewhere around like a 200K, 500K, 1,000K, and that's pretty much it. Okay. All right. So here we go. So the way that we can take into account how the temperature affects the expansion of a substance is through the thermal expansion equation. Even though this is an equation that looks, all right, simple enough. However, there is some things that you need to be sort of like understand how to use this one a little bit. I'll let you know what it is. All right, first thing first, you have a bar of material. Let's say you warm it up, right? For example, in this one, you heat it up using some, burning gun or anything. So initial length of this one is L0, L0. And then you assume that it's going to have the longer length in that particular direction. So you can take into account what is going to be the change of the length. Let me call it the delta L. That is the increase in the length due to the temperature change of the delta T. See that? So these two comes hand in hand. So you assume that there is a linear relationship between the change of the length, delta L, and the change of the temperature, delta T. Okay. And of course, you can imagine that. I mean, how big is this change of the length, the delta L? It depends on where you start your length with. That makes sense because it's sort of like it's expansion on top of the initial length. And of course, there might be another one that sort of like governs how this expansion is going to happen, how good or how bad this material is going to expand. You can name that the coefficients of expansion. Because right now we are looking at a single dimension is along the length. So what we are looking at is the linear. Every time you talk about the linear, that's one dimension. Okay. So what you are looking at this point is the expression that trying to calculate the change in the length of the material that have the initial length of L naught and has gone through the temperature change of delta T, and that material has the coefficient of expansion alpha. We use alpha for that. And that's it. This is a linear equation, easy to use, easy to apply, and you just calculate them. Okay, so the table that you are seeing right now, that gives you the numbers of that alpha for some examples, some materials that you are seeing over here. Okay, and the figure on the right, that's the effects from the thermal expansion. So when things expand, when it's hot, then they have a tendency to push each other, and then it's buckle and everything's just broken and everything turns bad. So the railway over here is bad because they forgot to put some spacing between the iron bar that make up the rail and all the stuff. So it's bad. All right. Even though I still have problem with this photo here, that's how come they complete the project without facing this problem beforehand. I don't know why. That I still don't know. Or maybe it's global warming or something. I don't know. At the time of constructing this one, there's no problem, but suddenly things get super hot and then turns bad over time. That could be. I think maybe it's longer span of time. I don't know. Okay. But anyway, one point to take from this table, I think this is the one. If you look at this one here, you have the steel and the concrete. Do you notice something here? Yeah. Yeah, they're sharing pretty much the same alpha. The coefficient of expansion are almost the same. That's a good thing because you use the concrete reinforced, steel reinforced concrete, right? Building the skyscraper and all the, building and construction and everything. So that's the thing that you need. You need them to be able to expand during the day and contract during the night at the same rate. So, I mean, yeah, the steel won't pop up from the concrete block and all this stuff, yeah. So that's what you want. Okay. So you want them to go hand in hand during the hot time during the day and then cool down. Then it's sort of like shrink down at the same rate as well. Okay. So that's a good thing. Right. Those engineer people knows this. They have to use this one. Now here comes the question, guys. Well, Ajahn, you only do one day. You do the linear expansion. But in reality, this whole thing going to expand in all directions. Not only the length, the height is going to expand, the depth is going to expand. So why don't you care about the volume expansion? Why you only take care of the linear or just the expansion in length? The answer is, yeah, I'm going to do that. And I'm going to do it now. All right. And before we do that, you guys look at this. How do you like this equation? Well, Dan, what kind of question is this? How do you like this equation? I know how do you like it? I like it because it's linear again. Isn't that cool? Yeah, it's linear again. But now you just change the length into the volume. You start with whatever volume you want. The delta T is still there. But then you change the alpha into, of course, you have to have another coefficient that take care of the volume expansion. So let's name this beta. All right. So the thing is, well, Ajahn, so from the look of it, it's same type of equation. It's still a linear equation. I mean, it's 1-to-1. Delta V relying on delta T. But do you notice something here? They look the same, but how come they look the same? That is my questions of the day. What is the question of the day? Because now we're going to dig a little bit deeper into the mathematics and just want to, test the familiarity with the mathematics, and the sort of like the things that you have done in the past. Okay, let's take a look at this, guys. I don't know you like this or not, but stick with me here. It's kind of fun. Okay, start with the length, the width, the height. This is the volume, right? Okay, so let's say at the initial temperature T naught, the volume of this bar is going to be the length, the width, the height. That's volume, no problem. Now you warm things up. Your temperature increases by delta T. So your final temperature is going to be T naught plus delta T. Now here comes the thing that you have already learned. Well, okay, now for the length, I can apply that linear expansion equation. The delta L that I'm going to get is going to be alpha L delta T. You guys with me here? So that's mean the new length is going to be the original length L plus the delta L, the alpha L plus delta T, the alpha L delta T. Cool. Same thing is going to happen with the width. You use the same equation, but it's a different dimension, but that's okay. Original width times the delta length. So it's going to be alpha W delta T. You guys, so far so good. Same thing is going to happen to the height. Original height times the delta H, the length that increased, alpha times H times delta T. So the new volume that you get is supposed to be the product of this parenthesis right here, right? Correct? And if you try to multiply them, that's no big deal. I can pull the common factor out. I have the L is right here. I have the W, I pull it out here. I have the H, I pull it out here. And they all have sharing the same common factor, 1 plus alpha delta T cubed. Cool. So far, so good?
Okay.
My question is this. How can you go from the cubes function back to nothing here? With me? So you guys see what I'm seeing right now?
Okay.
Of course, I mean, the volume is supposed to be cubic function of the length. And then you already saw that there's a delta T cubed in there somehow, somewhere. But then the final equation that we use for the volume expansion doesn't have any delta T cubed whatsoever. Here comes the thing. We use this expression right here. Now, how familiar with this expression to you guys? Have you seen this before? Maybe, maybe not. For those computer engineer or computer science people, probably have used this many, many times, I hope. We'll see. All right. But anyway, for those of you that don't familiar with this, that's all right. I can go through this with this simple one, the square. That's easy. That's a complete square function. So it's a หน้ากำลังสองบวกสองหน้าหลังยะบวกหลังกำลังสองยะ All right. You can still do cubed. I think that's still in your memory somewhere somehow. Okay. So it's gonna be what? หน้ากำลังสามยะบวกสามหน้ากำลังสองหลังอะไร whatever. Yeah. สามหน้าหลังกำลังสองยะบวกหลังกำลังสาม So this is good. I don't know how you guys sort of like memorizing this one, but that's what it is. And it still keep going. If you want, you can do 1 plus x to the fourth. You can go 1 plus 4x plus 6x squared plus 4x cubed, on and on, x fourth. But anyway, my point is this. This one, these three expressions over here, as long as x is small, let's say x is not that big. Somehow, let's say x is 0.1, for example. Then that x squared term will push the numbers back to the second digit. You guys with me? And the third powers term over here will push the numbers to the third digit, on and on. So this is sort of keep going. So as long as the numbers of x is small, the higher order term will get less significance. Things get even better if it's x is like 0.01. Wow, if x is 0.01, the second order term will push the numbers back to the fourth digit already. And forget about the cubed one will run all the way to the sixth digit. Does that make sense? So that's why all I can do is just like, oh, Dan, I'm happy with just the first term right here. I'm okay with this. That's called linearization.
Okay.
So you only keep up to the first order term and throw away the other terms that is very small value. And you say that's insignificant. So you can just sort of ignore them. That's why instead of keeping all the higher order term that makes the complication complicate, then I'm just going to keep just the first term that is still x to the first order. And here comes this approximation. 1 plus x to the n can be approximated to be 1 plus nx. Throw away the higher order term. And does this one works for us? Yeah, it seems to work because you have an alpha in here. And look back at the alpha, guys. Whoa, it's 10 to the negative 6 all the way here. Is that right? Okay, so that means this 1 plus alpha delta t is supposed to be a small number. So this approximation seems to be a good one. So that's why I can throw away that cube and turn it into just a linear function, and you have a number 3 in the front. Okay, and of course, by having this, now you can give the conclusion that this term that is the change of the volume, LWH, that is just your original volume, 3 alpha delta t comes into play. And that's it. This whole terms over here turn into 3 alpha v delta t. So now you can guess 3 alpha, that is your beta right here. And that's it. You're done. Okay, cool. All right. So that's what it is. And of course, this one only works if the expansions in all directions in the length, the width, the height going in the same rate. So that's why I have the name isotropic material. It's a material that expand equally in all directions, right? There are some material that doesn't do that, like, you know, some weird composite materials, some weird polymers or whatever. It might expand in one direction better than the other. But for the isotropic material like metal, yeah, it doesn't matter the width, the length, the height, they don't care. They expand in the same rate in all directions. Hello, yes. Okay, not talking to me, right? All right then. All right, so that's what we have. But what's the point at that? Okay, first of all, I just want you to see a little bit of mathematics today. Otherwise, then that's not going to be a lot of fun for physics class without mathematics. Second of all, now let's remind you what the approximation means. We're going to have a lot of, well, not a lot, or maybe it's just only some approximation come in the way from time to time. But the key point to take here is this is the type of the equation that is not a law. You guys with me now?
Okay.
It's not sigma F equal to MA. This is just the phenomenological expression. It's just the equation that you use to explain some phenomena in the nature, and then you just try to use a simple linear form to take care of that explanation. That's it, guys.
Okay.
All right, got that one? All right, so don't take this too seriously. I mean, in reality, this equation will not be exactly correct because you throw away the second order term, third order terms, on and on. So for reality or even some material, this equation might not even work. All right, but I'll just give you how physics work in the sense that sometimes you need some equation to explain some things that are going on in the nature. And this is how it's done. All right, and that's it, guys. If you okay with that, I have another, you know, calculus throw in without extra charge here, just for fun. Another way to look at this, if we want to attack this one from the perspective of sort of like a differential calculus and other stuff, you can start from this. You have a volume. Let's start from an easy one, the cubic volume. So you have length, width, height to have this equal length L. So the volume of this object is going to be L cubed. Now you say you want to figure out the change of the volume. That is the dV. You guys with me? this sort of familiar to you guys? Yeah. Differential change, a tiny change of the volume, dV. Now you can start using the chain rule because you want to know what is the change of the V with respect to the change of the length. So you do dV by dL and then you chain it to the dL. And everyone knows how to do derivatives. Yes, I hope. Yeah. 3L squared. That's the derivative of L cubed. Okay. And then now you can express this one using, here we go. Even though you did the delta L is equal to L, I'm sorry, let's start with alpha. Alpha L delta T, right, with the L naught there. Now you can transfer or sort of like rewrite this one in a differential form. You can say a tiny change of the length will be equal to the alpha times the length times the tiny change of the t. You guys familiar with this sort of differential ways of writing an equation here? Okay, very good.
Okay.
All right. And then the good thing about this one is, I hope you sort of like see the difference between these two equations. And every time you learn this in calculus, it's kind of annoys you, I know. But the point is this. When you do the differential, things go to zero. This is like super, super duper duper small. It's approaching zero. This thing approaching zero. So when you do this, it's actually good. The good thing is it's like things supposed to be super, super linear back in the infinitesimally small space. You guys with me? This is good. And because you're already there, you want to take care of the change. You don't need the subscript zero here anymore because that's your L right there. And when the dt happens, change of the temperature happens a little bit, the length will change by that bit, dl. Okay, so this is a good thing. This is a good thing in the sense that the differential form is almost, there's no approximation. It's good. It's good. All right, so you use that differential form here, and then now you can see that you can rearrange things. Alpha can be attached to the number 3 in the front. You have L squared here. You have L left there. It's L cubed. It's back to you. L cubed is just the original volume, and that's it. You can turn differential equation back into just a difference equation. Yeah, it's differential and difference. And going back over here, that is just not as good. All right, you're going down, that's kind of nice, but going back up, that's just your approximation again. Okay, so I hope this sort of like give you another perspective of how to arrive at this expression. But once again, they are all from linearization. You just keep things linear. You don't want to deal with the higher order term. You don't want square terms. You don't want a cube term. You don't want anything higher order terms. So you only keep the delta t terms here. All right. And by having done this cubic or having done the volume expansion, if you really want to take care of the areal expansion, the change in 2D, now you probably can guess the coefficients of expansion is supposed to be 2 alpha. And that is done.
Okay.
Okay, cool. All right, guys. I hope that's give you an idea how things, constructed. All right. This is not the law of nature or anything. Okay. So the table that's give you the volume expansion is given right here. And this one showing you some application, even though this kind of application probably obsolete nowadays because you use digital control now, you're probably not going to use mechanical control. But this one is kind of cool in the sense that it's called thermostat. In the device that you want to control temperature, and then you are not allowed to use electronics in that area, maybe super hot or super cold or whatever, then you still might want to resort to the mechanical parts. So this one is very clever. The way that they build this one is they use it's called bimetallic. So you use two types of metals that having different expansion coefficients. So when you go to a higher temperature, in this case, you can see that the brass is going to expand larger than the steel. So in that case, then this bimetallic strip will bend up. And then you can attach this to a switch. So this switch will depends on the temperature. All right. And then you can decide a switch for have this switch to turn on or off when the temperature is up or down, up to you. Okay. So this one is a thermostat. It's a thermal switch, let's say. Okay. But I think nowadays, for home use, you use electronics control device and everything, right? Okay, but this one is maybe 2 decades ago, all the air conditioners using this type of thing. All right, cool. All right, and just want to emphasize on the point that I was just made, saying that the expression is only for some material. One quick exception is right here in front of you. Water. Water is bad. Okay, water is not going to follow that exactly, because we know that the water has the highest density at 4 degrees Celsius. So that means if you start at that around 4, no matter which direction you go, you want to warm it up, you want to cool it down, the water will expand in both directions. All right. So that's just to make sure that you understand which expression is a law, which expression is just the, you know, an expression to explain something. Yeah. Maybe I talked too much already today. Yeah, I think. All right, guys, let's do some calculation, shall we? All right, that's kind of like still having fun, I hope. I don't know. No response so far, so good. All right, but anyway, for those of you that's waiting for something difficult, it's coming to you. All right, don't worry. All right, so this one is sort of like warm-up lecture. All right, and it's gonna peak around maybe the 3rd month or so. All right, it's gonna be a lot of fun. Okay, so let's look at some example. 2 spheres are made of the same metal, have the same radius, but one is hollow and the other is solid, guys. What do you think? So there's a hollow one and there's a solid one. Okay. The spheres are taken through the same temperature increase. Which sphere expands more? What do you think, guys? All right, it's not internet connection. The second one, okay, very good, very good. All right, just to sort of give you a comparison, if I have now a sheet, so it's a 2-dimensional, okay, and then the one with the hole and the other one does not. Same thing, right? So which one should expand more? All right, 2 answers seem to go with the solid one. Okay, and now let me throw the third question to this. Now let's only look at a single sheet and I have a hole in it, right? And let me warm this thing up, burn it up. What happened to the hole or the cut? What do you think? All right, so these are the sort of like the same sort of like type of questions. Shrink, okay, all right, okay, that's the same line of thought. Okay, now let me try this. So this one, there's a hole at the center, in the center. So it turns out instead of having a hole, I have another piece. But then instead of having the hole here, I'm just drawing, not cutting out just yet. I'm not cutting it. I'm just traced where I would like to cut, but haven't cut it yet. And then I burn this piece of the metal sheet again. What happened to this drawing? All right, just keep some motivation here. What happened to the drawing? All right, just kidding. So for this one, you probably answer is gonna expand, all right? You agree with me here? All right, so the point is, this one is easy to answer because I haven't cut anything yet. Eventually that drawing of mine, we're gonna expand along with the piece of the metal sheets. but this shouldn't be different from I have a hole here. So the answer is it's supposed to expand. Okay, that's one thing. So come down here. Now, once again, because we understand the thermal expansion from the microscopic level. So if I am a group of particles, maybe atoms or whatever, that is inside this metal, I don't think I will be able to tell that there is a hole here or not. Does that make sense? Because within this material, there will be millions of atoms. And I'm not going to be able to tell 1 centimeter away from me that is going to be already like a million molecules or million atoms away from me. That is that going to be like a hole or not? All it does is just it's do the expansion locally. They're going to expand locally. So my point is this: in general, no matter you have a hole or not, everything is going to expand because it happens in every microscopic locations on this material. Does that make sense now? Okay. So I would like to use the argument saying that each single or individual atoms in the material won't be able to tell the rest of the structure of the substance. It's impossible. So what it does is does locally. It's just gonna, hey, push away all the neighboring atoms. Hey, just get out of here and get a little bit further away from me, on and on. So the answer will be same. Okay, does that make sense? All right. And overall, all right, I can say, all right, in real life, it probably not going to be exactly the same, but based on the things that we have already established here, we only care about like the first order approximation down to the first approximation. Yeah, I would say they're all the same. Okay, so I would like for you to get, to think in terms of like you're doing an operation. When you increase the temperature, things expand. No matter the shape, no matter the size, no matter what it is, it's like you're doing like enlargement in the Photoshop. It's like you have a figure and you enlarge them. Everything in that photo get enlarged equally with the same rate, with the same ratio. Does that make sense? All right, so that's what it is. Okay, so think of it like you're doing a Photoshop and you have a photo, you want to enlarge them. Everything will go out with the equal aspect ratio and everything stays the same. Okay, no change. Okay, all right, so I hope I get my point across. Not too much, I hope. All right, let's look at the next example. You have an aluminum tube, 3 meter long, 20 Celsius. What is the length at 40 and at 0 degrees Celsius? All right, so this one, just to make sure that you know how to apply that main equation properly. Okay, so this is just the change of the length. Okay, and this delta T works both positive and negative. So don't worry, you can apply it. For example, if you start from 20, you go to 40. So part A, the delta T will be positive 20. In part B, the delta T could be negative. That's fine. So that means for the part B, things are going to shrink down a little bit. That's okay. Okay. And don't worry that, you're never going to go wrong with this because all you have to do is just plug in the value. So the delta L is going to be the alpha of the aluminum. We can look it up on the web or in the textbook. The L naught is just going to be 3 meter. That's your original length that you want to put in. And then for part A, you put plus 20 here. And then for part B, you put negative 20 degrees Celsius there. And then once you have that, you want a final length. Don't forget the final length. Let me put L prime. You have to use the original length first and then plus the delta L. That's what. Okay, so this equation will take care of the change of the length. If you really want the final length, just add on top of the original length. So because we are not doing anything differential here, let me put L naught right there. Okay, very good. This is plug and play problems, so that's easy to do. Let's move on. Try this one, guys. The concrete sections of a certain superhighway are designed to have a length of 25 meters already. Now the sections are poor and pure at 10 degrees Celsius. So this is a block. And of course, now we learned that we're supposed to leave some space between them. Okay. So there must be some spacing between them. So that's 25 meters each. That's 25 meters each, on and on. So what is the minimum spacing should engineer leave between the concrete block to prevent it from buckling? All right, so you want to be able to, leave some space. Let me call this like a X for now. That's a spacing that we need to supply. Okay, so first of all, when things get hot, all right, this block of concrete will expand. And of course, to be fair, it's supposed to expand on both sides, I guess. Okay, so let's be fair, like let's split that delta L into half-half. Because, I mean, it's supposed to go in all directions, right? Not only single direction. So what you have over here is you say delta L is just alpha of the concrete times the L naught times the delta T. All right, that's all you need to do. The alpha of the concrete, you can look it up in the table. Actually, we just mentioned about that. That's right here, that concrete around there. So let's pick that number, 12 times 10 to the negative 6. Okay, 12 times 10 to the negative 6. All right, so let me omit the unit here, so make it a little bit shorter. The original length is 25 meters. The delta T, because you pour and cure at 10 degrees C, but then during the daytime, it reached up to 50. So the delta T is going to be 50 minus 10. That's the delta T that it has to reach. And that's it, guys. What should be the X? So the X, the minimum spacing is going to be twice the delta L over 2, right? Because we suppose that the next piece of the concrete will expand delta L over 2 as well. So that is twice the delta L over 2. So it gets you back to the delta L. So whatever the delta L that you got from the first line, that will be your minimum spacing that you have to leave between blocks as well. Cool?
Okay.
All right. Of course, the question in the exam is going to be that easy. All right. So let's take a look at this. All right. Let's do 2 more, guys. I mean, just do 1 more and then we're done for the day. Sounds good? All right. We have the other one just for DIY, so you can do it yourself. But this one, let's use this as our last exercise of the day. Sounds like a plan?
Okay.
All right, guys. This is a challenge 1. You have a liquid with a density rho. Show that it shows. So that's good. You know the final answer that you're supposed to reach. Show that the fractional change in density for a change in temperature delta T is given by this expression right here. And what does the negative sign signify? What does it mean? All right, guys, I'll give you 1 minute head start. Whew. How are we going to start here? First, what is rho? It is density, right? Density. All right, everyone knows it must be the mass per volume. That's good. So far, so good. But now we want the density change. And then we want to link this change to the temperature. So the hint supposed to be, of course, we only learned this, the volume change can be written in terms of this simple linear equation. So this somehow has to relate. This equation has to relate to the definition of the density, mass per volume. But how? I think the easiest way, or I mean, I don't know, it seems to me the direct approach to this one is I would like to use some calculus here to help. And that will speed things up a lot because we would like to check for the change. So let me look at the change of the rho with respect to the change of the volume. You guys with me? I want to see how things go between these 2 parameters. So what I'm doing is I want to do, hey, what is the rho change? When you change the volume, that is the d rho by dv. So all I need to do is just take the derivative of this expression right here. M is constant, the mass does not change. So all you need is just take the derivative of 1 over v. Derivative of 1 over v is what? Very good. Minus 1 over v squared. You guys with me? Okay, all right. The m is still there. So far, so good. All right. Now, I can turn this into a differential form, just like what we did before in my examples over there. So I can say is the change of the rho is going to be negative 1 over v square mass dv. I put the dv to the right side, and this one turns into a differential equations. I mean, differential form. It's not a differential equation per se. Then now I can use this that already converted into a differential form as well. With me, guys? Remember, we can do this sort of like, okay, turn it into a differential change. So that means that dv over here can be put here. Nice. So let me put there beta v dt. Yeah, cool. So far so good. Now 1v cancel. Get rid of that. Good thing about this one is m over v itself is rho again. You see the final answer now? I can bring the rho on the right to the left. So it's going to be d rho over rho. On the right, I have the beta left. I still have the dt there. And from here, I can turn this thing back into the delta, just the difference, not the differential. So I can turn this into the delta rho over rho is going to be negative beta delta t. And that's it. I'm done.
Okay.
Cool. What does the negative sign mean? Of course, Ajahn, it comes from the differential change. Right here. It's inversely proportional. So that's why every time the change in the rho is positive, it will give you the negative change in the V. Okay, so that means, of course, in this case, you link it through the temperature. So when the temperature rises, the volume increases, but the increase in the volume reduces the change in the density. Because that's why you have a negative sign here, because it's the opposite direction change. Okay, and that is it for today, guys.
Okay.
Cool. So far, so good. All right. So I hope this one is not bad. Any comments or suggestions before we go? All right. So if not, I'll see you guys on Wednesday. Yeah. All right, guys. Have a good day. I'll see you soon. Bye-bye.